Thales theorem involves circles and inscribed triangles. And in particular, Thales theorem says that if one of the side lengths of your inscribed triangle happens to be the diameter of the circle, then the opposing angle must be 90 degrees. Thales theorem, what makes Thales theorem is they actually proved it, and he proved it using two facts. One of the facts that Thales used was that if you take an isosceles triangle, that is a triangle that has two sides of equal length, say this side and this side, then the two base angles, say here and here, actually coincide as well. And another fact they used, and this is one that most people remember from geometry, is that if you take a triangle and take a look at its angles, say alpha, beta, and gamma, then the sum of these angles, alpha plus beta plus gamma, is equal to 180 degrees. So we can use these two facts in order to prove Thales theorem. So let's get rid of this, and we'll establish that that is 90 degrees. So the idea comes from this. If you take a circle and this inscribed triangle, remember this inscribed triangle here is the diameter of the circle. So if we take a look at its midpoint, that is actually the center of the circle. Now the key here is to split this triangle. And what we do is we split the triangle by making another segment come out of the center and connect at this point. So this gives us three equal sides. In fact, this side we know is a radius because we just drew it from the center of the circle, but now this one is too, and this one. So this gives you two different isosceles triangles with these two side lengths being equal and these two side lengths being equal, which means that this, call it alpha, is equal to this, so we'll also call it alpha, and this, if we call it beta, is equal to this one, and we'll call that beta as well. And so here we use this fact about isosceles triangles. So now, if we continue, we can use the outer angles here, alpha, alpha plus beta, and we know what the sum of those guys have to be. In fact, so we know that alpha plus beta plus beta is equal to 180 degrees. And so we just use this guy as well. And that's a degree symbol. All right. So now if you look carefully, we have alpha plus beta twice. So that tells us that 2 times alpha plus beta is equal to 180 degrees. And finally, that tells us that alpha plus beta is equal to 90 degrees. But that's what we wanted to prove, because this angle here is actually alpha plus beta. So we proved Thales theorem. It didn't take a whole lot of effort. And so at this point, I think it's traditional to go find an ox and sacrifice it. All right, so before we conclude the video, I want to include one application of Thales theorem. And now this one comes from very much the 20th century mathematics, and it occurs in the field of Ramsey theory. So Ramsey theory is the investigation of unavoidable patterns. So basically, no matter what you do, there are some things that will always occur. So for instance, if we take the plane, and let's choose 3 colors, so RGB, and then I take every point in the plane and I color them with one of these 3 colors, right? I only have a blue marker, but you know, just imagine each one of these points has a different color, and not only these points I colored, but every single point in the plane. So all these guys up along here, you know, all these guys, every one of them has one of 3 colors. And so, you know, it could be red, it could be green, it could be blue, etc. And so, in the field of Euclidean Ramsey theory, which is basically colorings of the plane, or you know, Rn, higher dimensional Euclidean spaces, the idea of Euclidean Ramsey theory is that you're looking for certain things like shapes that could occur. Now there's a bunch of open problems in Euclidean Ramsey theory. They're actually pretty easy to understand, and I'll link to a bunch of papers, to various Euclidean Ramsey theory papers. One that has a bunch of open problems, another one, there's 3 papers by Erdos and a few other authors, just talking about theorems in Euclidean Ramsey theory that are interesting to read. And one of the things that people care about are what kind of triangles and other shapes you can find inside of a plane that's been colored in this way. So basically, people care about monochromatic triangles. So say we want to have these sort of triangles. Now, of course, there's always going to be some triangles in here. If you just choose 3 points, you can make a triangle. But the idea is that you can find certain types of triangles. Now, what we're going to be looking for here is we're going to be looking for, we're going to be showing that there has to be, for every 3 coloring of the plane, there has to be at least 1 monochromatic right triangle. And so, that's what we're setting out to prove here. So this particular proof that I found, actually I spotted on Stack Exchange, and this proof is due to Michael Biro over at the University of Connecticut, where he is an assistant professor in residence, I believe. So basically we're saying that if we color the plane with 3 colors, say red, green, and blue, then there exists a monochromatic right triangle. Now, of course, at some point we're going to use Thales Theorem in order to prove this. But this is going to come down to several cases, and that we'll explore one at a time. Okay, so this is the idea. Now, when we say monochromatic right triangle, what we mean is that the 3 vertices of the triangle, not counting the colors of the edges, are all going to have the same color. So in this case, maybe red, red, and red. Or green, 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 blue, blue, blue. We don't say what color they must have. Because it could be that we have a plane colored in 3 colors where only 2 points are red and 1 point's green, and then everything else is blue. And then in that case, you could obviously find a monochromatic blue triangle, but you wouldn't be able to find one that's, say, red or green. So we make no guarantees about what the color will be. We just say that it'll be monochromatic. Okay, so let's go ahead and get started. So like I said, we don't know how many colors, how many points in the plane are colored each one of these colors, but what we do know is by the Pigeonhole Principle that there has to be at least 2 points with the same color. So we're going to just assume, without loss of generality, that these points are red. It could be that the only points are green or blue, but the actual color doesn't really matter in this case, or the label of the color doesn't matter. So we'll just assume that we can find 2 reds. Now, let's go ahead and draw a line segment between them. And at the midpoint of the line segment, so we're going to call this point 1 and this point 2. And now at this point here, point 3, we're going to label this as being the midpoint of these 2 guys here. So this guy, we're going to have cases based on this guy. And so splitting it into 2 broad cases, so we're going to have case 1, P3 is red. And then case 2, we're going to investigate is P3 is not red. Right, so that seems pretty exhaustive, right? So let's go ahead and start with the first one. So here we're going to assume that the midpoint is red. So this is red, this is red, this is red. And remember, this is P1. So we're calling this guy P2. This guy we're calling P3. So what we're going to do is we're going to actually draw 3 parallel lines that each one is going to be perpendicular to this line segment. So here, doop, doop, and doop. Now, we can call this guy line 1, line 2, and line 3. Now, it could be that, all right, so now we have a subcase, right? So we have a case A, at least 1 point on L1, L2, L3, other than P1, P2, P3, is red, right? And in that case, we just take this guy here, and if this was red, then we could have a right triangle right here, and we're done, right? So case A would be done immediately. Okay, so now let's assume that we don't have case A. So then it leaves us with case B. Basically, no other points on L1, L2, and L3 are red, right? So that means that this has to be, say, all blue and green, right? Because those are our 3 colors, red, blue, and green. Well, that means that if we take L1, there has to be at least 2 points that have the same color. They could both be green, they could both be blue, but they couldn't be red. So let's go ahead and take this guy green, and let's take this guy green. So let's assume we have 2 green points. Now here's what's really neat, is if we take 2 new lines that are perpendicular to L1, 2, and 3, which means that they are parallel with this line segment, then we have these intersection points, right? So with these intersection points bring in their own cases. So we could have, let's call this case B1. It could be that all of our circle points are blue, right? Well, then we're good there, because if this is blue, the blue and blue, then this makes a quadrilateral that each has 90 degrees at each one of these points. And so then we can just go ahead and make our right triangle here, right? And so then we're done. So case B1 would be good. Okay. So now if we have case B2, where we have at least 1 circle is green, then if, say, this is green here, we have a right triangle as well. So we're good. And that covers case 1. So case 1 demonstrates that we must have a right triangle if case 1 happens. Okay, so now we need to go and talk about case 2. Okay, so now we're back on case 2, where so case 1 was P3 was red, so that means that the opposite of that case would be P3 is not red. So this is pretty straightforward. So remember, these guys we already determined red, P1 and P2, and we're saying that P3 isn't. Okay, so now why don't we go ahead and make a circle. P3 will be the center of the circle, and it'll be of radius that is 1/2 the size of the segment. So that means that P1 and P2 will actually form a diameter. And so you can kind of see where Thales Theorem might pop up here. But before we get to Thales Theorem, let's go ahead and talk about another point. So here we have another case. So another subcase. Again, we're just going to call this case A. So so it could be that no other point on the circle is red, right? So that means that they're all blue and green, and say green and blue. All right, so then what Michael Biro says that you should do is you should go ahead and make a cross in here, and choose two other diameters other than the one with endpoints P1, P2, and choose them so that they're 90 degrees to each other. So that gives us a collection of points here. All right, so now we're down to our circles again. Okay, so now we're down to two subcases. Okay, so notice that we haven't actually labeled the color of P3 yet. So why don't we go ahead and do that now? We'll just say it's green. It doesn't matter if it's green or blue, you know, it's just a label at this point. So we can have another subcase, and we'll call this case A1. We can say that at least two of the circles are green. All right, so this could happen in two different ways. In one case, if we have a green here and a green here, then we have three greens in a row, and then we can just use case 1 to finish. If we have two greens that aren't diametrically opposed, we have it like this, but then ta-da, we have a right triangle here. So then that's done. Okay, and then and now we're left with the second possible subcase, case 2, where we say that where we say at most one circle is green. Now remember, we already said that these points aren't allowed to be red. That means that these 4 circles, at most one of them can be green and the other 3 must be blue. So no matter which way we choose it, we're going to have a blue here, a blue here, a blue here. We'll have 3 on one side, and 2 of them will form a diameter. And so then by Thales theorem, since this forms a diameter, this angle must be a right angle. And so then, ta-da, so this time we use Thales theorem. Okay, and so then that case is done. And in fact, that takes care of case A. And case B follows pretty quick, and this is again by Thales theorem. So case B, we have at least one other point on the circle is red. Right, and so then let's say it was this point here, and then ta-da, we have, we know that this is a right triangle, again by Thales theorem. Okay, so Thales theorem actually proves something in what is called Euclidean Ramsey Theory. We have just proven that no matter what we do in coloring a plane with 3 colors, there is at least one right triangle somewhere in the plane that is monochromatic. So I think this is a pretty neat application of Thales theorem, and so, yeah. So before we go, I want to mention real quick the text by Patricia O'Grady on Thales of Miletus. You can see I picked up from my local library. This book is probably the most comprehensive book source of information you'll ever find about Thales. Everywhere else I looked only had a paragraph or 2 on him. This included history of mathematics books, as well as Bertrand's History of Western Philosophy. So Thales of Miletus by Patricia O'Grady is a great source for whatever you want to look at. But keep in mind, it's all from a perspective of a philosopher, so it's not exactly how a mathematician would describe him, but still very helpful. She also talks about the experiments of Lavoisier and others in sort of disproving the water hypothesis. Thank you for stopping by.
If you like this video, please push the like button and consider subscribing to my channel for more of the same. You can follow me on Facebook through facebook.com/thatmaththing. Please consider supporting this page through Patreon. You can find a link here and in the description down below.